we start off with thanking the organizer for letting us come here. As you can see, I'm not doing this on my own. I have representing this on behalf of my colleague, Dr. Hege Damlien, and myself. So, after the retreat of the Scandinavian ice shield, paleoenvironmental data demonstrate fluctuations in temperature and sea levels, as well as changes in vegetation, fauna, and marine conditions. How did human groups populating the Norwegian landmass in the early and mid-Holocene cope with these changes? In the course of several thousand years of environmental change, we find shifts in demography, settlement patterns, and lithic tool technology. But are these cultural and environmental trajectories related? The concern of this paper is to explore factors influencing transitions in material culture during the Mesolithic of Southern Norway. During the last decade, technological analysis of lithic assemblages has played a pivotal role in the Mesolithic research in the region. As such, the starting point for this talk is technological analysis of attributes in blade assemblages from 40 sites. We will here take an exploratory approach and investigate whether technological changes in lithic blade assemblages is related to climatic and/or demographic events by exploring different data such as C14 dates, lithic technology, and climate data. When studying material culture variation among Stone Age hunter-gatherers, there is one recurrent question. By what means did cultural traits change through time? In order to investigate this, we will rely on studies of lithic blade technology. Blades were the principal blanks used for tool production over large parts of Paleolithic and Mesolithic Europe. Variability in blade production indicates that hunter-gatherers were not tied to one production strategy, but could potentially choose between various reduction methods and knapping techniques. Studies of blade technology thereby offer an important step towards explanations of technological and social differentiation among hunter-gatherers and for tracking temporal and spatial continuity in change in cultural traits. Ethnographic studies indicate the hunter-gatherers are conservative on learning craft skills. This is largely due to reliance on learning strategies emphasizing vertical and oblique transmission related to craft techniques. This reflects conservative transmission modes that assure slow evolution. It is reasonable to assume that the mode of transmission of craft skills in the Mesolithic societies is comparable to those documented ethnographically. The archaeological record is generally characterized by continuity and conservatism in technological practice rather than change. It seems to be the constraint of existing practice to keep things the same rather than changing them. However, within long periods of stability, rapid changes can be documented in the archaeological record, often recognized as something new and different. So what should then be considered the prime drivers for change in prehistoric hunter-gatherer societies? Complex craft such as blade production requires time and practice to learn to perfect. Consequently, we can expect that transmission of technological knowledge dependent on social learning will vary in relation to demographic factors influencing between and within groups. Demographic factors such as population size, density, and contact is considered to play a determining role in learning and information storage capacity and have a fundamental structuring effect on the transmission and acquisition of information. Following this, technological continuity is dependent on regular contact between groups of adequate size being sustained over time, ensuring the transmission of knowledge and skills. However, if the group size is small and or less connected, the technological system is fragile and more exposed to factors such as cultural drift or to be affected by important events such as migration and environmental change. So one potential driver for change in the technological system is environmental changes and climate events. Hunter-gatherers live directly off the natural environment and respond to local changes in the ecosystem. This means that environmental changes can be reflected in the archaeological records in various ways, determined by the effects of the changes on the ecosystem. Even though climate change is known to affect culture and behavior, there is no one-to-one relationship between climate change and culture change. This can be illustrated by a few examples. Waddington and Wicks have recently suggested that a population collapse took place following the 8.2 event in northern Britain, but cannot demonstrate any technological changes in relation to the event. Robinson et al., on the other hand, has suggested that both socio-cultural and technological changes followed both the 9.2 and 8.2 kilowatt events in the Netherlands. And further, Manninen has argued for behavioral and organizational change, but no variation in population size in northern Fennoscandia following the 8.2 event. The examples demonstrate that climate can be a driving force for technological change, but also indicate that technological change does not automatically follow a climate event. The examples also demonstrate how climate is considered a major factor in fluctuations in hunter-gatherer populations. Recent studies have stressed the importance of marine resources and suggested that rich marine environments allow pooling of resources, thereby making marine Mesolithic hunter-gatherers less exposed to climatic variation. This is of importance here, as most Mesolithic sites in our region display a clear affinity to former coastlines and hence a marine adaptation. The Norwegian coastline also experienced an increasing marine productivity during the Mesolithic and can possibly demonstrate a different demographic pattern and responses to climate events than elsewhere in Northern Europe. So in order to investigate the long-term trajectories in lithic blade production, we have analyzed blade assemblages from 40 sites dating between 9,500 and 4,000 Cal BC. Technological and statistical analysis of archaeological and experimental data is used as a basis to predict knapping technique in the archaeological assemblages. To investigate the temporal variation in demography, we use a dataset consisting of 350 radiocarbon dates from southeastern Norway. The analysis demonstrates several shifts in the organization of lithic technology during the Mesolithic. And based on this technological analysis, we will have focus on changes taking place at 8,300 Cal BC and 5,700 or 600 Cal BC. The early Mesolithic blade technology is characterized by long-term continuity involving blade removal from one-sided platform cores by means of direct percussion techniques. The technology displays similarities over large parts of Northwest Europe. Profound changes in technological organization are demonstrated at the boreal transition with the introduction of blade production from conical cores and by pressure technique. None of the sites where pressure blade technology is documented holds any traces of early Mesolithic blade technology, indicating a replacement rather than an adjustment of blade tool-making practices. Furthermore, the analysis demonstrates that the pressure blade technology in southeastern Norway can be explained as deriving from northeastern technological context as documented in northwestern Russia and the East Baltic region. The relative sudden appearance and spread of technology allows for a hypothesis that the technology was introduced to southern Norway by arriving groups, and that the late pre-boreal colonization pulse of northeastern hunter-gatherer groups, as documented from northern Fennoscandia, continued deep into western Scandinavia. This human dispersal is associated with new manufacturing techniques for bone tools, as for macro tools, as Karine recently showed, indicating a collapse of existing local technical systems or even demographic replacement. The technology appears, however, to have been adopted by the local population in relation to intimate contact between different groups, a contact that is proven to have had a genetic effect. 3 minutes, okay. It is interesting to note that the technological changes also corresponds with the 10.3 cooling event. The event is detected in the paleoenvironmental records from several regions in Northern Europe, including Southern Norway, and is suggested to have caused the cooling of the Norwegian Sea, as well as re-advancing glaciers. Talavar et al. Have argued that the temporal distribution of C14 dates in eastern Fennoscandia indicates a population fluctuation and a pause in the northward colonization, a fluctuation linked to the negative effects of this cooling event. Conversely, the introduction of the pressure blade technology into central Scandinavia roughly corresponds with the melting of the last part of the Scandinavian ice sheet and the second colonization pulse, suggested as a rapid colonization by eastern pioneers after 8,150 Cal BC. Just have to hurry up a bit here now. So we're moving on to late Mesolithic. Several climate changes are identified during the Holocene, of which the 8.2 event is considered the most significant abrupt climate change after the Younger Dryas. This is of course detected in paleoclimate records in the North Atlantic regions and in southern Norway as well. The effect of this event on demography and cultural change is however little explored in southeastern Norway, and so far only an analysis including site counts of shoreline dated sites have been carried out. This indicates that there is no detectable decrease in the relative number of sites following the climate event, and neither does the C14 data show a decrease in dates following the event. Further, there are indications of a later cold episode in the North Atlantic dating to around 5007 to 5500 CalBC. This event is lesser known than the 8.2 event and was perhaps of a more local character. What is interesting in this regard is that around 5700 CalBC, a technological reorganization took place in southeastern Norway. Microbed production on handle cores by means of pressure techniques starts to dominate the assemblage from this date. And we also observed changes in the macro tool assemblages. And as argued by Egeland, as technologies before and after 5600 CalBC are very different. The C14 data also show a decrease in number of days in this period. And there is also a considerable gap in dates between sites with the different macro tool technologies. We should, however, be careful not to overestimate this decrease, as the variations in the C14 model in general is small during the Mesolithic, and most likely does not reflect severe variation in population sizes. I'm running out of time, so I'm just going to jump to the conclusions. The two technological shifts discussed here have resemblances. We see a sudden break in the blade and macro tool technologies, suggesting that new technological traditions was introduced to southeastern Norway during the middle and late Mesolithic. The shift we see corresponds in time with climate events that had effect on hunter-gatherers in other regions of northwest Europe. However, we don't see any direct link between climate events and cultural change in southeastern Norway. We hypothesize that the succession of several events at interregional scale led to the demographic and technological events in southeastern Norway. The changes might be environmentally underwritten, but cannot be seen as regional adaptive responses to climate change. Rather, the effect of the climate appears only to represent one part of the whole of a complex whole. The development is probably best explained by a combination of factors such as demographic, social, and economic change, as well as in historical and environmental constraints. Thank you.